Welcome to this comprehensive guide on the KRAS 3. We are going to explore four distinct ways to build a neural network. We start by importing NumPy, TensorFlow, and verifying our versions to ensure a stable environment. Once that is done, we generate a synthetic dataset using three variable nonlinear equation involving sines and cosines, adding a small amount of noise to simulate real world data. Then we will perform a 80-20 split. We'll perform a 80-20 split on our data to ensure we can validate our models on unseen data. Once that is done, before we use the high level frameworks, we will establish our mathematical baseline. We will define a manual mean squared error function and a numpy reference forward pass. So our architecture is consistent across all the all variants. So three we have three input, uh, 10 and 8 neurons using ReLU and 10H, and then one single linear output. So this is what we have defined here. Once that is done, this is our first variant of the assignment, that is TensorFlow from scratch. So in our first variant, TensorFlow from scratch, instead of KRAS layer, we will manually initialize weights and biases as tf.variable object. So we have defined here weights and biases as tf.variable object. So we have defined all the three layers weight and biases. Once the initialization is done, uh, we will do the forward pass function. So this is the most granular way to use TensorFlow, though it results in higher final test loss compared to more high optimized level methods. So we'll define the layer 1 2 3 here. We will compute the we'll multiply the weight and then add the biases manually for all the three different layer, and then we will test our forward pass. So once that is done, l- we'll do the training. And once we have defined our epochs, and for all the epochs we'll do this training where we will do the forward pass, compute the MSE, compute the gradient, and then manual gradient descent update we will do, and then we will print the progress for each epoch, and then we will test the evaluation, like the test data. So we can see, um, this is our training results. So initially on the first training the loss was 2.9, which has now came down to 1.5 final test loss. So this was our first method. Now second variant is TensorFlow within the built-in layers, that is subclassing. So the variant 2 uses model subclassing. We inherit from tf_keras.model, and we inherit from this tf_keras.model, and then we will use built-in layers, dense components which handle the weights initialization for us. So we don't need to initialize the weights here. Will it will use this dense layers and it will initialize weights for us. So once that is done, we will use a custom training loop with a gradient tape. So we have used this custom training loop with a gradient tape, and we will use Adams optimizer. We are using this Adam optimizer. So we will use this Adams optimizer leads to much faster conversions than our manual scratch method. So this is how we are doing it, and we can see the losses decrease from 0.69 to 0.16. That is a very uh, great change in the loss value. Once that is done, we will move to the third variant. The third variant utilizes the functional API, TensorFlow functional API. This is a standard for professional model building because it handles complex nonlinear graphs easily. So we will define this build model function where do keras.input. We'll define hidden layer 1, we will do hidden layer 2 using, we have given the extension function name, we have given the hidden layer name, and then we have passed the inputs. This input comes to hidden layer 1, and then this goes as input to the hidden layer 2 with the activation function as 10h. And then once that is done, here we are defining the number of neurons, the activation functions, and the hidden layer name and the input. Second, we are defining the second layer where we are defining the number of neurons, the activation function, the name, and the input. Then the output layer, we are defining the output, the activation function, and the name and the input for that output layer. Once that is, we have defined all these layers, we will create a model using keras.model, and we will give the inputs and output and the functional model name, and then we will return the model. So this is how we have defined using a functional API using the um, dense keras.dense layers.dense function. So this is how we define a model, and then we will print the summary of the model. Then we will train this model. So to train this model, we will do model.compile, and while compiling only, we will provide the optimizer and the loss method, and that's all. We just have to do model.compile, pass the optimizer, the loss function, and then it will train the data. And the history is mentioned into model.fit. You can do it, will print the history, and yeah, we can test it as well. So we can see the test results. The losses decreased. Now moving for the fourth part, that is sequential API. So finally we look at the sequential API, which is the most concise way to build models in Keras. Like the functional APIs, it uses efficient compile fit workflow, making it perfect for rapid prototyping and simple stacks of the layer. So here what we will do, we will define this function, and here we will do keras.sequential. In this we will define all the layers in a single pass. So layer 1 we will give the details, layer 2 we will give the details, and layer 3 we will give the details, and we will give the name of the model, and then we will return the model. So in a single pass we have defined all the layers, and then we'll define the training function where we will do model.combine, we will pass the optimizer and the loss function, and then similarly we will do the model fit to train the model, and then we will print some epochs out of this, and then we will test the evaluation, and then we will see if it handles the test in a list. So we can see the loss, it has decreased from 0.4 to 0.02. So this is the summary of comparisons of all the variants. So the first variant the loss was this much, the second variant the loss decreased, the third variant and the fourth variant. So loss decreased gradually for all the variants. All the variants use the same architecture, the same activation functions, the same loss method and the same data set, but still we can see the loss values are different for all the four variants. So let's conclude with a 4D visualization using a 3D scatter plot of our three inputs. We use color to represent the target value y. Comparing the actual plot to the predicted plot, we can see that model has perfectly captured the complex non-linear relationships in the data. You can see it's almost same. So this is the final complete tour of our completes our tour of the TensorFlows and Keras. We have successfully moved from manual tensors met to high level production APIs, achieving an R square over zero point 0.9 across the board. So that's all for this assignment. Thank you so much.